in the interest of time, I think we're going to get started. Thank you for all coming. It's truly an honor and big privilege to have him present his work here here with us. Professor Moghaddam is a William Power Professor of Mechanical and Aerospace Engineering at the University of Florida. He earned his PhD at the University of Maryland, College Park in 2006, and he was a postdoc for 3 years at UIUC. He, starting from his graduate studies, he worked extensively on boiling and the film evaporation that Yangjin is doing. He has worked a lot on boiling, on CHF enhancement techniques, and he has received numerous awards for his research and teaching, such as the Micro FIP Leadership Award for his impactful scientific contributions and leadership in fostering collaboration and innovation, and the ASME ICNMM Outstanding Early Career Award, and the University of Florida College of Engineering PhD Advisor of the Year. That's an awesome distinctive recognition. His work has been featured in different media outlets such as Data Center Knowledge and Heat Pump Magazine. He has published 150 plus technical articles, book chapters, and 20 patents. He has given 40 plus plenary keynote speakers and vision talks at different venues. He is a fellow of ASME and Ashari. And on a personal note, I know him when I was a grad student, and I used to follow his work. And actually, the thin film evaporation work that I did was inspired by his paper, which he published when he was a PhD student. So it's really an honor to have him here, and we look forward to a presentation.
Salman, thank you. Good morning, thank you for attending this talk. It's an honor to be here. I've really enjoyed my visit so far. Amazing science being pursued here and conversations I had with faculty. Today, I'm going to talk about the single bubble thin film and limit of phase change heat transfer. And I will touch one application for it, which is data centers. I in general work in thermal management, different companies, but the data center is the one that we have made most progress. This is about a third of my research portfolio, so I apologize if I do not have some other aspects, but I would be more than happy to have conversation about other part of my research. But this is Solomon's most favorite topic. So that's why I decided to put all boiling here.
Yeah, don't worry, we do bubbles as well.
Okay, perfect. So obviously, from the conversation this morning, boiling is a very effective heat transfer mechanism. That's why we have used in nuclear reactors such high heat flux boilers and across the industry for centuries, right? So now we have these modern applications that fundamentals are the same, but when you get to a sort of more of a confined space, microchannel, microscale, things start to become difficult. And just like we had in a nuclear reactor, we need predictability and safety, all those. And that's why we need to understand boiling. So some of the work that I've done in the past, especially expand radars, we have interest in development of two-phase cooling system for polytronics, and elephant in the room that everybody talks about is data centers. So boiling is wonderful. It's interesting science, but it's very complex. So add to phase change to turbulence flow, and that's where you get boiling, make it very difficult. So currently, if you look at the companies that I talk to, when they want to develop their heat sinks, they go through hundreds. I've seen sample 256. That's that, because they have to go through a lot of trial and error. There's no model for boiling. So if anything that we do to advance the science, understand the physics, and then develop a model, would definitely improves the time to market of these products. And I do believe that there's going to be a lot more of different technology that they use phase change and basically boiling. Boiling happens. We have two formats of boiling. This is a recent test that we did close to a critical heat flux that I will define. It basically constitutes essentially little micro pump that you have at the surface, and basically these things essentially generate, pump the hot liquid out, and there's also latent heat is going on. And you can admit that it's going to be a very complex process to model. And this is over a planar surface. Once you get to the structure surface, it gets exceedingly difficult. So when it comes to now got nucleation put in a microchannel, you move away from that single bubble and then interaction to more complicated configurations. Obviously, this is more or less, you could even model it through nuclear boiling from empirical models. But once you get a more complex phenomena such as merger, now this you can imagine that this is substantially impacting the bulk flow, not only bulk flow, but also the heat transfer near the valve. And as you put more and more heat, all of a sudden you go to a completely different regime, which is elongated bubbles. As I will show you, essentially there is based on lubrication theory, these elongated bubbles, as they slide, they trap a layer of liquid between the bubble and the surface, and that essentially is main mechanism of heat transfer. And then ultimately, if you have enough inertia for the fluid to move on, and then add enough heat, depending on the thickness of the film, you can get to this regime. If the film is thin enough, at some point you will have even nucleation season. So if you saw the nucleation and interaction in the previous slides, then you can, and then accept that that's complicated. The complexity is much more here because you go from one regime to another. So if you look at even two prominent models that have been developed by Moghaddam and Tomi, they're just focused on one mechanism, right? So the question is that can we really at some point, 5-10 years from now, have tools that can fully model this phenomenon? And even this is just a smooth surface. Can we add structure into it? Can you have all those? And then that's the mission. And I've been working 20 years, and I think that I should be working for another 20 years to get there. So what's the challenge? The community has, they have tried to do it for several decades, and more recently, microchannel, maybe 3 decades. There's a significant challenge to address this. And it's a measurement challenge. So you can have all sort of assumption for the sub-processes of the boiling, what controls the heat transfer. But when you put a model together, you have only the bulk data to compare. You really need to, if you want to develop a numerical model, you want to develop a machine learning model, you really, if you can essentially have a way to validate the model at a very small scale, obviously you get more higher fidelity data points. So what's the difficulty? So if you go back to the literature back in large tubes, so you apply a heater and basically, and you produce bubbles and you measure the surface temperature. And you are interested in developing an empirical correlation, right? So the heat flux that you apply to the surface, you that write down the numbers, is the same heat flux that ends up in the liquid, in average, right? And yeah, there might be some conduction along the wall, but if you design the experiment right, all the heat flux in average will end up in the liquid. But once you go to the micro scale, and now you're dealing with you're trying to understand this phenomenon. Let's say a bubble is forming on the surface and moving, and even if you apply constant heat flux at the surface, it doesn't mean that the heat flux is constant. Heat flux is changing within the solid in microseconds and milliseconds. Because let's say you have a bubble and you had all of a sudden thin film formation here, evaporated now. So this is insulated now. So heat will start going from heater to this location that you have an extended meniscus, and you get much, much higher heat transfer. So therefore, it has been difficult for the community over the past few decades to try to essentially interrogate these phenomena to measure what the actual heat flux is. So if they try to do conjugate heat transfer, it's going to be very complicated because there's not much essentially validation ways to validate that. So years ago, when I was a PhD student, I was struggling with this for years. And I was following what everybody else was following. And I wrote a paper and got rejected because it was just not the right way. What I was claiming was not the case. So the community was back in even down to basically to 60s, they decided to use a low conductivity substrate and apply the heater here. So the assumption was that heat will go less inside the substrate and will end up in the fluid. So now they know the heat flux. But the problem is that this is a simulation we did, which initially we assumed that we have a single phase heat transfer coefficient. And then we applied a 10 times higher heat transfer coefficient, assuming that the film comes over the surface at this location. And then all of a sudden you see a drop in surface temperature and heat starts to come from everywhere. So now, even if that process is sustained, it takes seconds for these processes to essentially continue. You don't even know the heat flux is coming from everywhere. So you're not really, you can use this tool to study boiling because boiling happens in milliseconds, as you will see. So as I was thinking these long nights, I came up with a completely different idea. And it was that instead of using a low conductivity substrate that everybody's using, I decided, why don't we use a high thermal conductivity substrate, right? And then have a very thin polymer layer all over the surface, and then limit the temperature change only to that layer. And so thermal mass here is orders of magnitude less than the thermal mass here. So therefore, all of a sudden you can increase the response time by a factor of 10 times. So instead of all this region going to temperature change, only this very small region goes to a temperature change. The rest of it stays at a constant temperature. So that was really at the beginning of being able to essentially do the measurement. So all we do is that we have a heat temperature sensor below this, temperature sensor above that. We have a heat flux sensor now that can measure the heat flux in real time with a very high speed. So then we started addressing, so I'm going to take you to a journey of what we've started to address. So if you look at the nucleation, so nucleation, heat enters the fluid, there's a layer forms, nucleation of the bubble happens, there is a film due to nucleation, film of liquid is entrapped below the bubble and essentially evaporates into the bubble, contributes in not only the heat transfer from the surface, but the growth of the bubble. Then you have bubble getting heat from the surrounding and essentially ultimately goes up and liquid bubble departs and liquid come and essentially revets the surface. So this was the subject of hypothesis for several decades that people say, okay, so what's the magnitude of these events? How much heat transfer do you have? Which one is the dominant? And some of the things that I listed for some decades. So basically we say, okay, so let's use that technology to address these questions. And in this case, I made basically central array. This is 2 layers. So heat flux sensor, top measured temperature, and then below that you see there's another temperature that I measured substrate temperature. And these are around cavities. So made different cavities so I can get nucleation at the right time. And then essentially bubble essentially grows, and then I measure exactly the heat flux at any step of the way through the process. So let's look at one essentially event that I've recorded. Sensor 1, 2, 3, 4, 5, all the way. These are the temperatures of these sensors. These things measures the bulk heat flux. So I want to be sure that I have the energy conservation. So this shows the temperature of the surface, top surface in millisecond. So in this case, as the bubble grows, appears on the surface and covers the first layer of sensor, the temperature very rapidly drops, indicative of a rapid cooling at the surface. As the bubble keeps expanding, it covers more and more sensors, sensor 1, 2, 3, 4, and essentially they experience very rapid, cooling the surface. As the bubble expands, the temperature of these sensors recovers, meaning that there is no basically cooling anymore. And then the bubble starts to retract, the contact line starts to recede and essentially depart from the surface. And then you see another set of events, this time in a reverse order. the essentially sensor 4 starts to cool down, and then the subsequent sensors. And then if you do it in, yes, we consider boiling to be chaotic, but if you see thousands of these exactly identical happening in the process. So essentially, I associated with this first event between the bubble and the interface with the microlayer evaporation, and associated the second stage with the transient conduction based on all the data that we have. So if you look at it in the context of heat flux versus the time, you see these spikes are at the interface of the solid and the bubble, indicative of the microlayer evaporation, and then essentially the transient conduction essentially happening there. So this allowed me to, for the first time, come and actually take over an area size of a bubble to differentiate how much of heat is transferring due to microlayer evaporation, how much is happening due to convective transient conduction, and how much heat is happening to for liquid convection. So so what we realized that at higher temperature, essentially a substantial fraction of the heat is through microconvection, liquid agitated. And that's a more recent result from Matteo Bucci's group, MIT, that they did IR and they tracked the bubbles. They also came down to the conclusion that even in bulk, this was a single bubble scenario, but they came up with that 60% being transferred into liquid. But this essentially laid down the foundation for that physics.
And to my students, this is the work that actually inspired the PhD work that I did. The first time that I did this microlayer evaporation is when we started thinking thin film evaporation in my lab, literally after reading this paper.
Thank you. So then, so they obviously, in 2012-13, I tried to translate that work into microchannel because everybody started to doing microchannel at the time. There wasn't such a prominent discussion about the implementation in data centers, but my group and some other group, they have started working. So what we did, we essentially made a lab on a chip where you could generate bubbles at will from a nucleation site by having a pulse heater. And essentially we have different heat flux sensors, different direction to measure stuff, and heat flux sensors on the silicon substrate. And this is what it is. So basically you could go and essentially apply a pulse in this artificial cavity with the heater, and you can produce bubbles. And as they move, synchronize images and the data, you can read the heat flux at any part of the surface. You could manipulate this voltage such that you get larger bubbles, and you can produce essentially elongated bubble flow. We produced wavy annular flow and different regimes, and essentially based on the different heat flux and mass flux that we have.
And you have like sequence of sensors on this side.
Yes, so yeah, exactly, 50.
Yes.
So we collect more than like about 1 million data points per second. So let's say, look at this, let's address some of the things. Obviously, there are a series of papers that I will be happy to discuss with you. Let's look at this sensor 35, right? Where the tip of the elongated bubble moves over the surface. This shows the temperature. Remember, I was telling you that the temperature at the interface of the silicon and the polymer layer stays constant, always stays constant. What drops really this surface temperature. So again, when the essentially elongated bubble moves over the surface, you see again rapid cooling of the surface, and then we stay that way. And then essentially the microlayer evaporates, the liquid evaporates, and then the surface temperature recovers. And then as you go and the bubble moves all the way, so at the end, this is rather dry now, not fully dry, but basically dry because these corners are still dissipating heat. And then the trailing edge of the bubble moves over the surface and quenches the surface, and then you get another event. So if you look at it, essentially, then you have thin film evaporation, dry out, and transient event, and microconvection. It's amazing how you start from here and end up here in a process that people think chaotic. So this was the first, we published in 2015, and essentially the details of analysis is this more recent paper, was the first direct measurement of all the events and characterizing. So notice that we had thin film evaporation, underneath the bubble, and that was not a prominent mechanism of heat transfer, but here thin film evaporation became prominent mechanism. Remember, transient convection was on the order of convection and on the order of thin film evaporation, no longer. Transient conduction does not play much of a role in a microchannel, right? And essentially, this was the different mechanism that I'm going to break down a little bit more. So there was question in literature that contact line has a very basically high heat transfer, heat flux relative to the rest of the surface. So we actually put sensors that are here. As you can see, as the tip of the bubble moves over the surface, all of these three sensors, 1, 2, 3, where they experience the thin film, the temperature drops. Sensor 23 is really where the contact line is, and you don't see an outsized essentially heat transfer. And I discussed that in my 2009 paper, that even though that heat flux is high, but it's over 0.3 micron, so it cannot really have an outsized impact on the heat transfer itself. So basically, so here again, so here we showed that the impact, and then as the bubble essentially moves, then at some point these contact line moves back and back, and then ultimately even this sensor 22 is impacted at some point in 20 millisecond, 15 millisecond, and you see a little bit of increase drop in temperature is associated. So you could answer a bunch of questions in terms of exactly what happens as you move forward. Let's say we have channels with this different aspect ratio. So we proved that it's a known fluid dynamic phenomena. If you are going from a square cross section and going to high aspect ratio, as if you are squeezing a balloon, and what the force of balloon is surface tension. So what balloon does is that it's going to fight against you. It drains these films. So high aspect ratio means thinner films. Thinner films means that high aspect ratio, higher heat flux rapidly. But thin film also means a less amount of liquid. So when it evaporates, very quickly dies down, whereas these thick films gives you less heat flux, but over an extended period of time. Right? So some of these things that are when you measure these things and analyze, oh, this makes sense, but then it was not so much obvious before the measurements.
And these surfaces are flat or straight?
They're smooth surface. We are really at the infancy of this thing. That's what I think, that is a 20 years of chance to do things more and then essentially collaborate with this wonderful university and elsewhere. And so basically we started looking at in different governing equations, and what we really realized that up to a certain capillary, you can, to some degree, based on what fluid mechanicians did, Berthelton particularly in 1960, it's a balance between viscous forces and surface tension. So capillary is a good, up to certain capillary, you have some predictability, particularly in this is square channel. And obviously it was developed for round, but if you start going to essentially high aspect ratio structure, you start deviating from the existing models. Just give you very quick.
With that one, the bread trend, it shows that it's a 2/3 scaling with the capillary number for a bubble. Is it on a heated surface the same? This is evaporating, part of it is evaporating, the thickness.
Yes, so basically Berthelton developed his theory for a square cross section.
Yes.
Sorry, a synchro cross section.
Yes.
And people later on, if you go back beyond 60s, for hundreds and hundreds of paper, people decided to actually find they did even numerical simulation to find out that what's the basically thickness of liquid and thickness. So what happens when surface tension is actually squeezed? It pumps the liquid to the edges. So that's why it's much thicker as you go through the. So and that was rather simple to model. Well, it's fascinating modelings that you see efforts, but rather possible to model analytically. And that's what we have. But the focus of this case was we did the experimental data on this. We decided to focus on the delta.
but his modeling applies for, even if the surface is heated and there's evaporation, is still applicable.
That's an amazing question, which I will address it here, because for a long time, people say it's boiling and people do adiabatic tests and there's a disconnect, and I will address that question as we move forward. Just give a very quick observation and say, what is the current state of science that we believe and what should be done next? So we did an experiment, these are adiabatic experiment. So basically, Berterton assumed essentially a profile, essentially a circular profile, and then solved this Landau-Lewis problem. And when you start deviating from that, you see that the bubble tip becomes like a bullet, and you deviate from the solution because inertia plays a role that you're not factoring in. So that's why basically at the lower capillary and low Reynolds number, you can still predict from modified Berterton, but as soon as your Reynolds inertia goes away, you can clearly see it. So it's amazing that now when we look at the boiling, it's as if now we know a different language. We look at it and say, this is deviating from Berterton theory. And now, so what you need to do now, you have to solve an Navier-Stokes equation with the inertia term, right? So which is really something that we recently under NSF and on our project, we started one of my colleagues that is a classical fluid mechanician. We are trying to really do a direct numerical simulation and then move forward and train a machine model that understand all these things related to. So one cool thing is that, as I said, I mean, you change the channel size and you think that things will drastically change. But if you look at it from in the framework that I see, we see with this device is that this is the thickness of the film, this range of capillary for 300 micron, 600 micron, 900 micron. If you divide it by the hydraulic diameter, they all collapse on one line. And that's very much consistent with the lubrication theory that easily scales with, essentially, if you look at the expression in the literature, it's based on delta divided by hydraulic diameter versus the capillary, and that's what it is. So when you then you start moving into higher inertia fluid, way past the regime that we talked about, then you start getting into wavy annular flow, where you get these ripples over the surface. They have different characteristics. We published a paper on that one with different aspects of it, discuss it, map it. And then you go from there to the annular flow, where you essentially, again, we published a paper on that one, and we differentiate what are we seeing, why we are seeing it, and what are the implication in some of the what people see in the heat sinks. So, this is first time in this presentation that I'm going to now address one of the key questions that I brought up in my abstract. So we are doing microchannel boiling, but the question that is always in people's mind is that how far I can go with microchannel heat transfer coefficient, right? I mean, if, let's say chips become much more, people that I talk to NVIDIA and Vertiv, and they ask, how far can we go? Obviously, there are enhanced structures, and we're not talking about enhanced structures right now here, but we could be talking about extended structures that are very tight. So we learned that if you make the channel smaller and smaller, narrower and narrower, the film thickness declines. So it makes sense to assume that if the thickness declines, the heat transfer coefficient increases, right? So we decided to actually do an experiment, and we did at channels of different heights. These are not structures, these are just sensors that are, the schematic is just, it's not representative. So we decided to, and there was some folks from Purdue and Georgia Tech, they sent a fluid. We wanted to see why they are not getting to the heat transfer coefficient that theory suggests. I said, if there is a 1 micron, 2 micron layer of fluid, the heat transfer coefficient should be 1 order of magnitude higher than they have observed. And why is that the case? So what we did is that we had these bubble arrays now that we can essentially produce here. This whole test setup is 200 micron by 200 micron. So we can provide bubbles at different frequency, and we can do it in a way that we can always get a film, as more frequent film formation over the first. And what we found was so fascinating is that if you get all those different channels that we tested at different conditions, and even to get the average, and then put it on a heat transfer versus H. That is, this is order of magnitude more than what is reported. All our data stays essentially above the single phase, and below this showing the hypothetical heat transfer coefficient for this thickness. And so basically, as I said, the boiling is complicated, but once you understand different elements, is that essentially frequency comes to play. So if I am able to sustain that amount of thickness over the surface constantly with the technology, right? So I can get extraordinary heat transfer coefficient. And this is essentially proof that we have for this case. And even tight structures, if the fluid distribution is right, that can definitely give you a high heat transfer coefficient. So to answer Solomon's question is that, so we do in the community, people have had access to less complicated experiments, which involves adiabatic experiments, right? But people don't necessarily give the same amount of credit to those experiments because boiling is not happening. So what we realized here was that when you have basically film formation happens in microseconds, tens of microseconds, but the entire evaporation happens in milliseconds. So you could essentially even assume that the formation of the film is adiabatic. So you can go now, remove the heat transfer and go and actually understand the fluid from a completely fluid mechanic point of view, and then actually through the experiment. So we started years ago a significant effort to really understand the concept of instability in the liquid films and different kinds of instability that basically by carefully controlling the quality and the film liquid flow rate and gas flow rate. And we basically, if you look at regime maps in flow boiling, people refer as different kind of regimes. So what we did, we identified 4 prominent regimes. And then since then, we have been trying to essentially correlate that to really fluid mechanic variables rather than we stand here in the flow regime map and so on and so forth. So let's say in this case, what we figured out that this what is typically called churn flow, it's a superposition of these waves and this kind of wave, and I will tell you where it happens. So we had these periodic wavy the waves that we had that happens at the higher liquid velocity, low gas velocity that are mostly here. And then we have these sort of churn flow that people call in the literature in the flow boiling called solitary wave. When you increase the gas velocity, essentially causes significant shear, and essentially the fluid starts to turn and pick up from the main essentially film flow. And then if you're in between, you can have a combination. So that's what we had. And then if you're at sufficiently low velocity, then you have a basically stable flow. So basically, and that's and there's a paper that goes through all of these. What's the amplitude of these waves? How does it relate to the energy? And then what are the force balances that is in the review process? And then will get published soon. And then started a couple of new projects with a colleague of mine to go and use comprehensive, direct numerical simulation modeling and develop machine learning model based on these high fidelity data. I want to switch to something fascinating. Probably among all these things, this is my most favorite subject. And taking you to about a century ago, where Nukiyama is the father of the classic boiling. Essentially, after all these bubbles, you get to a point that he observed that the heat transfer from the surface no longer increases, right? And it became the inspiration for many in the field that what is the mechanism of CHF? And for a few decades, the chemical engineers, mechanical engineers started extensive studies to figure out why this phenomena is observed, why the rate of heat transfer from metal to a surface is limited. So two prominent essentially theory was, one was hydrodynamic instability theory was proposed by Kutatalase, and he gave a non-dimensional number. And then formalized by Zuber that he formed the correlation around it. And if you have not read Zuber thesis, it's a beautiful read to do. And so basically, the idea is that the source of critical heat flux is away from the surface, is in the fluid. So the gas is moving with such a velocity that essentially these liquid, essentially pathways that are coming back, are the interface between the two becomes unstable. So then you cannot get enough liquid to come back. So really, vapor pushes the liquid to on top, and then you get to the critical heat flux. So in this case, the scientists were surprised, if you look at the literature in that era, that, well, it's purely hydrodynamic. It doesn't have to do with other factors. So, but fast forward in 1996, the Safian's group in Europe, they came up with a different explanation. They said, you know what? So if I have a bubble forming, we see bubbles formation even to 95% of the critical heat flux. He said that basically this vapor generated interface is pushing the liquid back, right? And the surface tension wants to bring the interface back. So it's a fight between the two. If you get to such a temperature that the evaporation rate is very significant, then the momentum is generated is such that it just, the contact line cannot bring what wets the surface cannot come back. And so essentially, they call it evaporation momentum theory. And then people, different places that were doing experiment, sometimes they see this phenomena, sometimes they see that phenomena. Conley-Karp developed a correlation, and people were using it to describe the same. What did never satisfied me was two very fundamentally different physics associated with one experiment, and they predict the same thing. And happen to be predicting the same thing. Something that is the evaporation momentum, right, happens at the surface, has to do with the interface properties. And the other one, hydrodynamic, they give the same results. So basically, that was on my mind until we got an NSF program and started doing interesting experiment. So the experiment was that basically, I argued that if you stabilize the hydrodynamic above the surface, then whatever limits, the question is that what else is limiting the heat flux? So we said that let's go from here to there and then to here. So keep reducing the width of the heater such that there's just one liquid going up, one gas is going up and liquid coming from the side, right? Let's do that. And then we picked sort of this is the thing. So the width of this heater is, length of this heater is 10 millimeter. So we went to a 10 by 10 that people do to 2 to 1 to 0.5. I will tell you why we took 2, 1, and 0.5. So if you look at it, so we tested water, ethanol, and FC72. 2 is below water capillary length. 1.67 is essentially is the ethanol basically capillary length. So 1 and 0.5 are below that. And then with 0.5, we go below the FC72 capillary. Now look at the data, how fascinating the data are. So if you start with ethanol, with the capillary length was 1.67, right? And you do a 10 by 10 heater that everybody tests, right? As a function of the pressure. So it actually, you can predict it on a flat sprayer surface using Zuber theory. Okay? So now you go to a 2 millimeter, which is right above the capillary length. You go to 1, and then you go to 0.5, you see no change. So once we reduce the essentially width, but when we reach below the capillary length of the fluid, you see no change in the basically CHF. So let's do for water. So water is 2.73. So if you do 10 by 10, that's you get consistent with essentially hydrodynamic theory, Zuber.
10 by 10 is the heater size, or
10 by 10 heater size. 10 by 10 heaters. 10 millimeters by 10 millimeter. So now reduce one dimension to 2 millimeter. and then you get much, much higher, 4 times higher heat flux. So go to 1 millimeter, no change. Go to 0.5 millimeter, no change. So we realized that once you go below the capillary length, then all of a sudden you get a cap. You no longer have a higher heat flux from the surface. So let's look at FC72. So if you go again for a 10 by 10 millimeter, a large surface, you get consistent with Zuber. As you go to 2, 1, half, you keep increasing. Experimentally, for us, it's not possible to go below 0.5. If you do it, I do believe that we have capped out with FC72, and no observation about that. So we said, okay, so now, if you take all those data and get all the CHF value and divide it by the CHF maximum that we did, regardless of the heater, regardless of the fluid, regardless of the pressure, it comes out on this beautiful curve, which is that it starts from where Zuber limit is, and then all of them. So we believe that this is obviously associated with the 10 by 10 millimeter surface. And each one of them, when we narrow it, it's a different hydrodynamic state. It's higher than Zuber, but it's still a hydrodynamic limit. And ultimately, you get to this number that you can never go above once you get to that thing. So we said that this must be a surface limit, that what people discussed in 90s rather than what people did not think about it in the 1930s, 40s, and 50s, and the rest. So we went back to Conlicker and then looked at how come that his model predicts the same number that everybody else did, just like Zuber. And we realized that he made an assumption that the bubble is a cylinder, essentially. So we redeveloped the model for a spherical. And if you do that and you use experimental number for contact angles, you get a nice prediction for water, for ethanol, and FC72. So basically, the hypothesis was examined by looking at those experiments. And if you take the right model and don't try to force it to the experimental results, but the experimental results that are collected at the right regime, then you can see that essentially you can predict the thing.
So Kandelicker's model is assuming infinitely longitudinal.
Yeah, it's a cylindrical thing. And that geometry gave that 4 times different and allowed to fit it into the existing data. So you might ask, well, I'm not convinced. I'm not convinced that this is a cool experiment, but I still believe that there is, I need more validation. So how about if I do this validation, which is that I put a hydrophobic membrane and the bottom is a hydrophilic, and then the bubble comes in and the reaches on the surface wants to devet. The surface tension essentially moves basically grabs the bubble and takes it. That's why it goes from a spherical to a cylindrical. It means that there's a significant force pulling the bubble from the surface and exits. So this is a hydrodynamically stable scenario in large scale, right? This is a hydrodynamic stable situation in large scale. And then we said, okay, so now we are going to do a test. We put even surface structures on this. And then there's a discussion in the literature that sometimes people suggest that heat transfer surface area is impacting. Some people say leakability impact. And we say, well, why don't we do this? We do on a planar surface, number one. Then we do a test where we keep the surface area constant, increase the capillary wicking, and then let's keep the capillary constant, increase the surface, right? So as we did, we started, this is the limit of the membrane that you cannot go beyond, which is certain, this pressure essentially has certain amount. So if you go through essentially different surfaces, the one that has the highest capillary, essentially wickability, is substantially higher. But once you start putting force, pressure, and squeeze these bubbles and liquid anyway, squeeze bubble out and liquid anyway, it's ultimately going to, the effect of difference due to basically wickability goes away, but they come at the same number. So when we reach that number and say, why they came up at the same number roughly? And you say, because they have the same surface area, right? You say, okay, now let's keep the capillary constant and increase the surface area. So as we increase the surface area, we went right back to increase marching up in CHF, meaning that this phenomena was surface limited. We squeeze the bubbles out, we squeeze the liquid in, and the heat trans CHF increased, but we capped out because all the surfaces had the same surface area. Now, when we increased the surface area, we saw a direct relation between the surface area and the CHF. So what is fascinating is you look at this in the context of the literature with the surfaces that are completely different in size. So when you divide the CHF by area, they are roughly 400 to 500. Remember, bubble in water for the narrowest basically heater was 400. So here you get, I believe that the extra heat flux is because pressure is helping the contact line to move forward and the membrane. So the anomaly is a little bit, not too much, is this very tight surface that I think that we could not pump the liquid enough to get to that heat flux. But what is fascinating, the liquid surfaces that are vastly different in terms of the properties, they are showing exactly the same thing, which is basically close to the pool boiling scenario of a narrow. So we, at the time in 2017, I did predict that that's a surface phenomena. And then once we essentially did a recent study, then we could connect the dot and say that this is the same number, and it makes sense that you see the same phenomenon. So you might say, well, this is science, and then how do you go from these fundamental science to practice? So I'm going to spend maybe 10 slides for the remaining time, 6-7 minutes, very quickly go over the how do you translate some of these science to one application? There are other applications that we're working on, but let's talk about data center. So what is the difficulty in data centers is that air-cooled data centers that are prominent, essentially type of data centers, is that essentially cold air from these raised floor data center architecture goes inside these essentially racks, and then hot air gets out and essentially goes to air handling unit and goes to the chiller and then the cooling tower, right? So from a heat transfer point of view, your heat transfer, and you see that there's going to be a lot of thermal resistance at each interface, from chip to air, from air to this liquid, all of these. So there are a lot of delta T. So the industry is trying to do this and is doing this. So liquid cooling. And probably years ago, nobody would have imagined that this does not look like a computer, right? It's a mechanical room. And this gigantic pipes, a few inch pipes that pump gigantic amount of basically liquid into this, is because board has such a thirst for AI power. And then these racks are in 100 kilowatt. They're now thinking about 300 and 1 megawatt racks. Enormous amount. Data centers that are 1 gigawatt. The projection for compute is that it will exceed every other metrics that we do for energy consumption. So this is an example of how a data center will look like. This is single phase. The question is that when now we are running into the amount of liquid that we can send you these size of infrastructure. Remember at the beginning of the conversation, I said phase change is good. Why? Because you can have essentially a small amount of mass, if you can essentially, and high transfer coefficient with high influx. So the question is that, can we, and then everybody, when you see data center and cooling, and then talk about phase change, because single phase is water, right? It's a hard thing to compete with refrigerants with water two phase. So if you basically think about the refrigerant, all of a sudden everybody talks about PFAS situation, refrigerants and their environmental impact. So it's a dilemma that industry is trying to address. The question is that, can you have a water-based cooling system, entirely water-based? And that will address lots of challenges in the industry. So it's amazing because water is such a fantastic fluid. It has 6 times more thermal conductivity that directly transfers to the heat transfer coefficient. It has 15x latent heat. And that is enormous. So meaning that with a little water flow rate, you can actually cool a rack completely. And then essentially, but the challenge is that water boils at 100 degrees C. If you start going to lower pressure, the vapor expands so large that at some point the performance even drops below that of the refrigerants. So the question is, can you address that? So obviously the heat sink you saw, because we exit immediately that massive amount of vapor through the membrane. So obviously that was a breakthrough. There are also system level challenges. So if you have an entire system working at 40 kPa and you have this 2-meter rack, you have 20 kPa difference between top. So saturation pressure is different. So how do you address that? And then essentially sub-ambient operation. You need serviceability. One server is not working, you pull it out and put a new one. And then now air goes in and your condenser stops working and saturation pressure is different. This is a very challenge. So people just always walked away from thinking about water. And then once we had the heat sink for years, we sat down with the leaders in industry and figure out how can we address these kind of things that they are basically addressed. So let's look at the water. It's just this off the chart, that membrane-based scenario relative to the heat flux. So in long term, you can address really the heat flux issues as well as a high heat transfer coefficient. But the question is that can you really address the system level issues that we discussed? So just an example, so we tested a chip with this heatsink, and the total temperature difference between the backside of the chip and the vapor is roughly 6 degrees. Right now it's like 30 degrees. So you can really get the heat out at such a high temperature, and you can go to much. So really it's transformative. You could maintain the backside of the chip at 1,000 watt chip, which is the latest generation of NVIDIA that will come shortly to the market. So we have basically are able to keep that at basically 80 degree with fluid that is roughly at 74.
So they already have the chip out with
So
1,000 watt.
EV300,
Yeah,
so which is not in the market yet, but it will be soon.
1,000 watts over.
So it's 1,000 to 1,200 watts. And also heat flux matters because it's how what size it is. So basically, the other challenge that we never talk about, if you have these two-phase, two-phase flow is a function of pressure drop. So if you have a constant pressure, and then you have one chip, one GPU is generating a certain amount of heat versus the other, you get essentially a significant pressure increase. And obviously membrane mitigates that, but you still get maldistribution. So what is beautiful about this membrane is that the liquid, if you apply constant pressure, hydrostatic pressure, liquid stays in these things separately, and essentially heat cannot be applied at any rate. And liquid only evaporates when the heat is applied. So each one of these GPUs can essentially work at different rate. Also, the vapor is coming out at 100 degrees C. So for the first time, it allows to have the condenser inside the rack itself, even save the data center space. So
and these membranes are hydrophobized.
Hydrophobic. They are Teflon, porous Teflon.
I see.
Custom made with a manufacturer that we have, because they have to be very high permeable. The ones that are in the market, they're not permeable. So this work is done in board.
Is this the work you've done with the ARPA-E project?
Yes, it started as a fundamental science back in years
I know
ago,
you had the,
but then ARPA-E has allowed us to team up with a large team, which I'll describe,
yes.
and then allowed us to essentially translate it. So this test is done in Boyd Corporation, where they have actually developed a mechanism to deliver liquid to each server exactly at the same pressure. So if you want 3 kPa, you can deliver all 3 kPa. So there's no difference between top and bottom. The other thing is that they have developed an NCG control system. If you take a server out and replace, and then you have a little bit of air ingress. So there's a system that processes for some minutes, essentially takes the air out and purges from the system, and system essentially continues as the system is operating. So this is the essentially server that we have built and essentially shipped, and essentially is being tested, and which is a 12 kilowatt server with copper heat sinks. And then we have vision to let loose less copper, but this is just focus on really proof of the technology. So now we are in the stage of scaling it up. That was a small model, 3 servers, 36 kilowatt. So now Boyd has made a 12, so it's going to be a 144 kilowatt rack. These are the manifolds for essentially vapor and the liquid. And this condenser, believe it or not, water has such an incredible heat transfer coefficient that this in-rack essentially condenser can take care of all that thing. And we are even envisioning that if you go to a 300 kilowatt rack, we can have 2 condensers. We go through even higher a half a megawatt, it can be do like 3 condenser systems. So it's a very scalable system, completely water. And so the difference between this and other technologies is that this rack has everything. It has the condenser, it has all the elements, it's rolled into the data center, and essentially you plug it into the primary loop. So the difference between the air cooled that essentially you get so many delta T and then you have to have the chiller operating is that we can extract the heat at 70 degrees. We can easily release that heat to the ambient or essentially use it for different purposes. So it's if it happens that our reliability and material concerns are addressed, it will be transformative because it completely negates the use of refrigerants and it has a very high efficiency in terms of performance. And then we have done an analysis in terms of it has very positive implication in terms of the even initial cost because it's saving that does across the data center and the cost of the electricity. With that, I would like to acknowledge the students that had a huge impact on this. They helped me invent the heat sink for the membrane. Sam and Adam, they were primarily responsible for the microchannel flow, and Suhas, the CHF new discovery, and Stephanie tight channels that she has worked. And then the progress with RPI, I have 120 years of phase change experience with these leaders in the industry, and Patrick is helping with reliability and the rest of team packaging of the electronics, some publications, and I will thank you for that.
Thank you. Good, excellent. Welcome, Albert. Good. Question for Professor Moghaddam. Yes.
Yeah, I have a quick question. So, kind of how do you define the macro channels? Is that defined by the weight of the channel? I think it might be related to your size of your bubble, right? So,
Can you repeat the question?
I mean, how you define the macro channels?
That's a very good question. So basically, actually, that's a separate talk by itself. That essentially I've given part of it different places. So we published a paper a few years ago, which discusses that very concept. We start with the history of how they define microchannel, and then we are going to publish another paper, which is essentially about the transition from nucleation bubble to elongate. So in our opinion, microchannel, we define it when you transition from macro-scale behavior to micro-scale behavior and from heat transfer point of view. Two things that matters. Number one is that in microchannel, when the balance of force that we did shows that gravity starts playing less and role and at some point essentially dissipates, that essentially makes the film more uniform. So it's a surface tension dominated phenomena. And then they also transition from essentially nucleating bubble to an elongated bubble regime. So between that paper and what we discussed and what we are going to publish for FC72, we believe that 600, 700 micron channel is a break between the two regimes. Based on all these, basically not just simply because of size or whatever, based on the change in physics of heat transfer and fluid dynamics. That's how I think it should be defined that way.
So if we use different fluids, that definition will change a little bit, right?
But yes. As I said, it has to be focused on you transfer from nucleate boiling regime to thin film regimes, and then thin film also essentially be uniform and non-uniform. And it's different between different fluids. We recently published a paper in 2025 in IGHMT that we essentially tried to develop a model based on non-dimensional parameters. And we tested our model that was primarily developed based on FC72 with another, I think, R134A paper, and actually was able to predict the transition between the two regimes. And so I would love to others to take that model and apply it for different geometries, different sizes and fluids, and see to what degree it is channel size and fluid dependent.
Good, excellent. Another question. Yanjin is working on micro layer evaporation. So any question? Albert is interested with the manufacturing and data center cooling. I think we had a conversation. Any question?
So I would be happy to, I have lots of additional
Yes.
slides. If you want a brief 1-minute question about aspects of the one particular aspect, I might be able to pull a slide and essentially say, this is what matters. Go ahead.
Me and Albert will learn each other.
Yeah, thank you very much for the very nice talk. So just out of curiosity, near the end, for the data center rack cooling, you mentioned that the water, two-phase flow water boiling flow, the pressure was under sub-atmospheric.
Yes.
Was that a particular reason because of the, is that because of the?
So ship has to be maintained at 80 degree. And so the liquid has to be below that.
You know, that?
So, and then interestingly, if your heat transfer technology is not high, I mean, it doesn't give you high transfer coefficient, then you go to 60 and 50, all of a sudden you lose all the benefits. We have this fascinating range that allows to work, but you need a heat sink that has high heat transfer coefficient, and that's
So 80 degrees, you're okay.
80 degrees, so you have to be below that. And the vapor volume rapidly increases.
Any question? Yes, I have many questions that we'll discuss in private later. Any last minute question?
I guess I can ask just one general question.
Yes, Biruk is working on immersion cooling, so I know he will have questions.
Does the fact that like water can be conductive be a concern for like using it instead of like refrigerants for like FC7 units?
So this applies only in closed systems.
Yeah.
So I'm not suggesting that we can put the board in a water system. Basically, the immersion cooling with oil and refrigerants, as long as they do not have both electrical and material impact. Because the GPUs and these things work at a particular frequency, and the dielectric property of the fluid is also important. So water is not what I suggest for immersion cooling. So it basically, unless you have solutions in other ways and some particular application or what, but for me, water is inside the heat sink. But I mean, some people are trying to figure out how they can coat the boards with parylene and other approaches, and basically, as I said, it's just, I have to see the whole solution.
Right.
I have to see the whole, and also it has to be under sub-atmospheric again, because the boiling is different. But water is a fascinating fluid. If you can work it out in any configuration. Did I answer your question?
Yeah.
Perfect.
And we'll have more opportunity to ask during the lab visit. This is really fascinating talk. Thank you very much. We enjoyed the talk. It's excellent. And let's thank the